Hi, in this video, we want to take a look at simple linear regression. Okay, so simple linear regression, we've got two variables and we want the simplest mathematical relationship that we can have between those two variables. Well, what is the simplest mathematical relationship we can have between two variables? A straight line. So, think about, the college algebra you went through, think about, elementary, middle school algebra, high school algebra. You studied a lot on straight lines. And so we're going to use this fundamental mathematical function relationship to describe the relationship between two variables. Now, we can use this for the purpose of prediction. We can use a simple linear regression model for the purpose of understanding the relationship between two variables. And we can also use simple linear regression for the purpose of controlling the dependent variable where we can alter the independent variable. All right, so regression analysis is a statistical method that allows us to examine the relationship between two or more variables of interest. For simple linear regression, we only have two, the independent variable and the dependent variable. In its simplest form, linear regression, we aim to model the relationship between two variables by fitting a linear equation to our data. The steps to performing a linear regression are as follows. All right, so first and foremost, I'm going to have my model for the situation. So my model is that, so I'm going to say this incorrectly for the moment, but this is how we think of it, is that y is equal to a constant, our intercept, our y-intercept, plus slope times our independent variable. And so this is how we think of our model, y equals mx plus b. Now, we're dealing with data. Data never perfectly, or data virtually never adheres strictly to the model. And so what we're going to do to address the aspects that our model does not account for in the data, we're going to put on a little error term on there. All right, so the linear relationship between two variables x and y are generally represented with this equation. Think y equals mx plus b from high school algebra plus an error term. Y is the dependent variable, x is the independent variable, a is the y-intercept, b is the slope, and epsilon is the error term. Now, most of the time, this is technically not necessary, but most of the time, we're going to assume that epsilon is normally distributed with mean 0 and constant variance with respect to x. Now, when we do this, we must have that mean 0 and constant variance with respect to x. But technically speaking, if I want to fit a model, I don't need the normally distributed. We'll need it for hypothesis testing. All right, so after I just established this is my model that I'm interested in, next thing I'm going to do is estimate the coefficients. If you'll notice here, I'm not nailing down what alpha or beta are. So alpha and beta are the constant coefficients. And here I just say, hey, this is the mathematical relationship from like a general function point of view. I haven't nailed down the actual equation. So what we're going to do next is that we're going to need to estimate. All right, so the coefficients of coefficient A and B are estimated using least squares method, which minimizes the sum of squares of the residuals. That is the difference between the observed and the predicted values of y, and the estimates are given by these equations. Now, technically, this should be a b hat, and this should be an a hat, by the way. But we'll talk about that more when we get into the evaluating our estimates. So here, what we've got going on is that I'm taking x minus the average of x, y minus the average of y, and then I'm multiplying here and then adding up. This is actually the covariance of x and y. Now I'm dividing out by the numerator of the variance of x. Okay. And then here, we're setting it up so that to find a, after I've estimated b, I put the average of b and the average of y into this part of the equation. I treat epsilon is equal to 0 and put x bar, y bar into the equation, and that is how I'm going to estimate a. All right, so x sub I, y sub I are the observed values of our variables. X bar and y bar are the means of the variables. Now, the next thing that we do, we assess the goodness of fit. Now, there are tons and tons of ways to assess the goodness of fit. My opinion, my personal opinion about this is that it doesn't really matter how you address the goodness of fit, but you absolutely need to do it. There are tons and tons of different techniques. Different statisticians will tell you different techniques are better than others for certain reasons. There's advantages and disadvantages in every possible direction. The main thing is that you have to assess the goodness of fit. So let's say you're talking to one statistician and they say you should always use this technique. The other one says that you should always use this technique. My opinion, the technique is not as important as just doing it. Some way, some shape, some form, assess your goodness of fit. So we typically assess the quality of fit using the R-squared statistic. The R-squared statistic is by far the most well-known method. There has some shortcomings, it has some problems, but it's well-known and it's well understood specifically by those with like a moderate statistic background. And because of that, so like psychologists, sociologists, people who do not have a deep statistics background, R squared is more than likely what they learned in class. And so they're going to accept that better than other techniques. So my recommendation is to use whatever your audience will be receptive to. And so R squared represents the proportion of variance accounted for in the model. So the proportion of the variance for the dependent variable that is explained by the independent variable. And we compute this as the sum of squares residuals. So that's the sum of squares error divided by sum of squares total. And then it's 1 minus the fraction. And here's the formula for sum of squares residual. And here is the formula for sum of squares total. And R squared equals 1 means that the model explains all the variability of the response data around the mean. Now, the next thing we're going to do is do inferential statistics. So here, if it's applicable to my problem, to what I'm working on, like why I'm doing these calculations in the first place, I might go up and start doing some hypothesis testing. And so specifically, number one hypothesis to check in simple linear regression is to check to see if the regression coefficient is equal to 0. So here we'll be testing this. And so what this means, if b is equal to 0, if this is my equation and b is equal to 0, then x is not in the equation. So I'm checking to see, does x actually provide informative value for y when I run this hypothesis test? And so this is by far the most common one when we're doing regression. Now, the alternative hypothesis is that b does not equal to 0. And this means that if b is not equal to 0, then x explains some portion of the variability in y. That is, x has informative value for our target variable. And typically, we use a t-test for this. And then we also want to assess the assumptions. All right, so whenever I'm doing statistics, I have assumptions about what I'm doing. And if those assumptions are grossly wrong, I can't trust the output. My conclusions could be incorrect. So the validity of a linear regression model requires certain assumptions about the variables used in the model. It is important to assess these assumptions and ensure that my assumptions are not violated. So our assumptions are linearity, that means that the model is the correct model, independence between observations, homoscedasticity, so we have constant variance the variance of the epsilon is constant with respect to x. And the last one is normality. Normality we don't need for fitting the model, but I need it for hypothesis testing. If I'm going to be doing hypothesis testing or certain diagnostics, I need normality for my results to be coherent. And there are far, far, far more complicated types of regression that's possible. We'll talk about multiple linear regression, and another type is for logistic regression when our y variable is not a numeric. Oh, something I need to say about this: y for this model, y needs to be a numeric variable, and more than likely continuous. We would prefer for it not to be something like counts. Most situations, we would ideally like to have y be like a normal distribution, but that's not really needed. And when I say normal, I mean normal with when x is a fixed value. All right, so now let's interpret our simple linear regression model. So here, we're taking the simplest algebra equation I could possibly get into statistics, and we're going to try to interpret what's going on. So we're going to interpret the coefficients. So the coefficients represent the relationship between the independent and dependent variables. The intercept A is the expected value of y when x is equal to 0. Now, so this is the point where the regression line crosses the y-axis. Now, you'll notice that I use all independent variables x here. That's for when we do multiple linear regression. I wanted consistent language. Here we only have one x variable involved, but next video we're going to kick it up a notch and we'll have multiple. So I wanted consistent language. Next one we're going to look at is the slope, which represents the amount of change on average that we'll have in y when I increase x by 1. If b is positive, there is a positive linear relationship between x and y. So when b is positive, as x increases, y also increases on average. Conversely, if b is negative, there's a negative linear relationship between x and y. As x increases, on average, y will decrease. The magnitude of b indicates the strength of this relationship. The larger the absolute value of b, the stronger the relationship. Now, we're going to assess the goodness of fit. So the first one that we're probably going to look at is R-squared statistic. We call this the coefficient of determination, and it measures how well the regression line fits the data. R-squared is between 0 and 1. A value of 1 means that the model explains all of the variability of the dependent variable. And a value of 0 means that the model explains none of the variability. Generally, the closer R-squared is to 1, the better the model fit to the data. However, a high R-squared does not necessarily mean that the model is appropriate. For example, if the underlying assumptions of the regression the underlying assumptions of regression are violated, a high R-squared can be misleading. Furthermore, R-squared always increases as more predictors are added to the model, even if the predictors are not statistically significant. So this is a major aspect that we have to be mindful of when we get to the next step of multiple linear regression. We start throwing in more predictor variables. It works out that mathematically, if I start taking additional data and just keep on throwing it into a regression model for multiple linear regression, my R-squared will always increase. I could be throwing in junk variables and increase my R-squared. So this is a problem. Mathematically, we have to watch out for this. So we always have to basically do avoid the garbage in, garbage out when we do our modeling. Now, next I'm going to check my assumptions. And so in order for my conclusions to be valid, these assumptions must be correct for the real situation I'm modeling. First one is linearity. This is just saying the relationship between the variables is that linear equation that we had previously. That's just saying that I have the right equation to be fitting. Next one is independence. And so here, the residuals, the errors are independent of each other. And next one, oh, so we also need independent and mean zero and constant variance. So homoscedasticity, the variance of the residuals is constant with respect to x. And then normality, the residuals are normally distributed. Violations of these assumptions can lead to misleading results. So it's important to check these assumptions using diagnostic plots and tests. Finally, it's important to understand that correlation does not imply causation. Even if a significant relationship is found between two variables, it does not mean that changes in one variable will cause a change in the other. Other variables not included in the model may be influencing the relationship. Good example of this is that as ice cream sales go up, crime goes up. And so maybe if we commit more crimes, we could sell more ice cream. If we sold more ice cream, there would be more crimes. They're related to heat. And so because of this aspect, we can see a correlation, or we can see a very good looking linear regression model when we might be prone to reaching an incorrect conclusion. All right, so now something I can do, I can run ANOVA for testing to see if my model is worth using. All right, so the analysis of variance, ANOVA, can be used to test the overall significance of a linear regression model. In simple linear regression, the ANOVA tests the null hypothesis that the regression coefficient is equal to 0. It's going to be more complicated when we get to the next video. For now, this is just saying b is equal to 0 is what I'm testing when I run ANOVA on simple linear regression, one predictor variable. The alternative hypothesis is that b is not equal to 0. The null and alternative hypotheses are as follows. The null hypothesis is that b is equal to 0, and this says that the independent variable x has no effect on the dependent variable. The alternative hypothesis is that b does not equal 0, and so what this is saying is that x has informative value towards y. And how we handle this? Well, it's ANOVA. I'm going to be doing an F statistic just like we do with regular ANOVA. We're going to compute an F statistic, which is the regression of the mean squares regression over the mean squares error. And so here is my F statistic. And so notice I'm taking two measures of variance, making a ratio, and then I take the degrees of freedom and I find my p-value. And so mean squares regression is my sum of squares regression divided by the degrees of freedom of the model. Mean squared error is my sum of squares error, the difference between model value and observed value, divided by degrees of freedom for the error. So SSR is the sum of squares of regression. And so this represents the variance that is explained by the model, and it is the difference between the model value and the mean of the dependent variable. Sum of squares error, this is the sum of the square differences between observed and predicted values of the dependent variable. And my degrees of freedom are associated with the regression model and residuals respectively. And so here, this is how we set up our ANOVA table. We have a source of variation. So our regression row, our error row, and my total row. We have our sum of squares, our degrees of freedom. So I divide this by that to get this, divide this by that to get this, take this ratio, get my F statistic, and then boom, I compute my p-value using the degrees of freedom. If f is significantly larger than 1, then we have evidence against the null hypothesis, and we conclude that the regression model has a significant predictive capability. Remember to check the p-value associated with the f statistic. If the p-value is less than our significance level, typically 0.05, then you reject the null hypothesis and conclude that at least one of the coefficients is not equal to 0, meaning that at least one predictor variable has informative value towards our dependent variable. Now, ANOVA, when we get into the more complicated setting of multiple linear regression, ANOVA just checks to see, is there one or more informative variables in my collection of variables? So ANOVA checks to see, do I have one or more informative variables? When I only have one variable, it's just checking to see if that one variable is informative. If I want to check individual independent variables, I'm going to run hypothesis tests on the individual coefficients. And so I'm going to have a lot more tests when I run this way. In general, you're going to do ANOVA first and check to see, hey, I have something worthwhile here. Now I'm going to start checking to see which ones are worthwhile and informative value. Now for the purpose of simple linear regression, the test I'm about to talk about with my single x is that it will be equivalent to just doing ANOVA. Either one works, whatever works better for you, whatever your stakeholders are more comfortable with. So hypothesis testing for the coefficients in a linear regression model involves assessing whether the coefficients are significantly different from 0. This can be done using the t-distribution. I have a series of videos on linear models where I completely flesh out the theory of running all of these tests. And so if you're interested in the theoretical aspects of linear regression, that playlist will go knee deep and upside down into this material. But here, I'm just giving you the punchline. All right, so for this coefficient hypothesis testing, the null and alternative hypotheses for the slope and the intercept are as follows. For the slope, the null hypothesis is that b is equal to 0. That is to say that x has no informative value towards y. The alternative hypothesis is that b does not equal 0, which means that x has informative value towards y. For the intercept, our null hypothesis is that a is equal to 0. That is to say that our line passes through the origin. The alternative is that a does not equal 0 and the line does not pass through the origin. Most of the time, statisticians don't even really care about the intercept hypothesis testing, and we usually don't even look at it. In situations where I've had trouble with fitting or overfitting, I sometimes will drop the intercept. Typically, I don't, though. All right, so to test these hypotheses, we're going to run a t-statistic for each coefficient. And so we have like a generic formula. We're going to take our estimated value minus the hypothesized value for these hypotheses tests. Beta sub 0 is equal to 0. And then I take the standard error of the estimate. So I take estimated value minus the hypothesis test value in the null hypothesis, and then I divide by the standard error of my estimated value, and that gives me my t-test statistic. So beta hat is the estimated coefficient, so this could be A or B. Beta sub 0 is a hypothesized value that, as it appears in the null hypothesis, typically it's going to be 0. And then our standard error is the standard error of our estimate. And so we have two formulas for our standard errors. So here's the standard error of the slope, and you can see that I've got something that looks a lot like the variance of y divided by something that looks a lot like the variance of x. But notice that I don't have like two denominators going on, but I have just 1 over n minus 2. And now here, my sum of squares error for the intercept, I'm taking the variance of x divided by n square roots, and then multiplying by the standard error that I have here. If the absolute value of the t statistic is large or equivalent if the p-value is small, then we reject the null hypothesis and conclude that the coefficient is significantly different from 0. This suggests that the corresponding predictor variable is statistically significant in predicting the dependent variable in the regression model. All right, so now let's talk about assessing the goodness of fit of a simple linear regression model. And so what we want to do, we want to examine how well the model explains the variation in the dependent variable. And there's tons of ways to do this. Which technique you use is not as important that you actually check this. So the first one is R squared and adjusted R squared. I prefer adjusted R squared. It's basically just a modified version that takes into account how, makes it so that overfitting can be spotted a little bit easier. Something that I typically use, if these two are far apart, that's an indication that I've overfitted my model. There are numerical methods for measuring how well the regression line fits the data. The R-squared value, also known as the coefficient of determination, represents the proportion of variance in the dependent variable that can be explained by the independent variable. It ranges from 0 to 1. 1 indicates perfect fit. 0 indicates that the model explains no variability in the response variable. And it's just sum of squares residual divided by sum of squares total, 1 minus that. Now, the adjusted R squared basically takes into account the number of variables that we're using. And so how I usually use this is that if these two are, if there's a significant difference between them, that's an indication of overfitting. Now, residual plots, this is an important one. This is one that I will spend personally most of my time on, is looking at my residual plots to evaluate my model. So residual plots are graphs that display the residuals on the y-axis and the independent variables or the predictor variables on the x-axis. So residuals are going vertically on my scatter plot, and the independent variable or the predictor variable or the predicted values on the x-axis. If the plots in the residual plot are normally dispersed around the horizontal axis, a linear regression model is appropriate for the data. Otherwise, a nonlinear model may be what we need to do. Another option we could use, instead of a different model, we could just kind of do a transform on our x and y, which technically is a different model, but it's pretty close. So I could transform x, I could transform y, and then rerun the regression. I might get a better model. Now, the F statistic in ANOVA can be used to assess the goodness of fit. If the F statistic is significantly large and the p-value is small, then we reject the null hypothesis in favor of the alternative and conclude that the regression coefficient is not equal to 0, which indicates that I have a model worth working with. And for checking the assumptions, it's very important that we check the assumptions in linear regression. These assumptions are linearity. So the relationship between the x and y variable is a linear equation. Independence. So the residuals are independent of each other. I don't have like an autoregressive aspect. I don't have like any trend line or anything like that. Homoscedasticity. The variance of the residuals is constant with respect to x. And normality, the residuals are normally distributed about the predicted, or the residuals are normally distributed. Violations of these assumptions can lead to basically these problems with our model. So we want to make sure that everything's as solid as possible before we launch a model. Now, how we assess this, my opinion is that the graphical methods are the most important methods for evaluating a model. It's more subjective, but if you want to truly see what's going on, you got to do the plots. Our plots are our main tool in regression, evaluating our models. All right, so let's talk about assessing the assumptions of simple linear regression. All right, so the reason why we're doing this is that we want to make sure that we have an unbiased, consistent, and efficient model. Our assumptions are, once again, linearity, independence, homoscedasticity, constant variance with respect to x, and normality. The relationship between the independent variable and the dependent variable needs to be a straight line equation, and this can be visually inspected using a scatter plot, where we put the independent variable along the x-axis, the y variable along the the dependent variable along the y-axis. If the relationship appears nonlinear, we could use a data transformation, or a nonlinear model might be what we want to use. Now, next one is independence. So we want the residuals to be independent of each other. The error needs to be independent of each other. This means that the residuals for one observation are not related to the residuals of another. This can be checked by looking at the residuals versus time plot or the Durbin-Watson test. This is mostly relevant for time series data. If residuals are not independent, it suggests that the model is missing a key variable, or it's not properly handling the time or spatial structure of your data. This can be a very complicated situation to work with. I have a video in my time series playlist talking about what to do when we have auto regression in our residuals. It is well and truly beyond the scope of the class, but it's a good video if you're interested in this. Now, homoscedasticity, constant variance with respect to x. We want the variance of the residuals to be constant. This can be visually inspected using a plot of residuals versus the fitted values. If the residuals fan out over time and form a cone shape, heteroscedasticity, so here, heteroscedasticity, different variance is present, and we have a violation of our assumptions. Usually a transformation on the variables or a weighted least squares regression will solve this problem. Typically a log transform or a square root transform will fix it, depending on what's going on. And then the last one is that the residuals, we want them to be normally distributed. This can be checked using a histogram or a QQ plot. Statistical tests such as Shapiro-Wilk can also test this assumption. If the residuals are not normally distributed, it might be necessary to use a nonlinear transformation of the dependent variable. Violations of these assumptions can lead to invalid inferences and predictions. Therefore, proper diagnoses should be conducted when working with a regression model. If the model violates any of these assumptions, there are several strategies we can employ. These include using nonlinear transformations, adding an interaction term if I'm using multiple linear regression, or polynomial terms higher degree. So instead of having just x, I could have x squared and x in the model, or considering a different model structure altogether, or using non-parametric regression techniques. In some cases, bootstrapping can also be useful when model assumptions are not met. Remember, the goal is not to prove the assumptions, but to assess them, knowing that all models are imperfect. By understanding the ways in which your model is imperfect, you can provide appropriate caveats to your inferences and predictions. All right, so simple linear regression with R. Let's go ahead and use MTCAR's data set. I'm going to look at miles per gallon depending on weight. So my Y is miles per gallon. My X is the weight. And so now I'm going to fit a model using the linear model function LM. And here I can see that here's my intercept, and here it is the coefficient. So as weight goes up, that -5 tells me as weight goes up, miles per gallon goes down. Here is my multiple, or here's my R squared, here's my adjusted R squared. These are relatively close, so I don't think I have an overfitting problem. My hypothesis test for the intercept using the T test is statistically significant. My t-test for the slope is statistically significant. All right, and my ANOVA test, here's the degrees of freedom. The ANOVA is statistically significant, and you'll notice that in simple linear regression, this only applies to simple linear regression, I get the same p-value. That's not a coincidence. All right, so our absolute most important tool for assessing a regression model is visualizations. And so here I'm just plotting weight and miles per gallon. And so if I did not have this line here, I would look at these dots. I'm thinking, yeah, maybe there might be, there's kind of a line looking here. So yeah, I think it's appropriate to fit a linear regression model. Now, if you look here, you see this gray band. This gray band is the confidence interval for what the average value of miles per gallon will be given the weight of the vehicle. And so what's going on is, remember, we don't truly know what the average would be for a given weight. Anytime I'm working with data, I don't really know what's going on. If I knew what was going on, I wouldn't be doing statistics. All right, so let's say the weight is 4. This here is my 95% confidence interval for the average miles per gallon for vehicles with a weight of 4. The blue line is my estimated average. So let's assess the goodness of fit. And so previously I printed that out. The reason why I'm using redundant code in the video, because up there I wanted to talk about the coefficients and I kind of jumped the gun. But with the summary function, I can get the t-test for the intercept, the t-test for coefficient, and I can get the f-statistic, the f-test off of there, and I get r squared and adjusted r squared right off the bat. And so that's really nice for us. Now here is the r squared value, which we can extract from the summary function using the r dot squared slot. And we can get the adjusted r squared using the adjust dot r dot squared slot. And here we have those two differences. And now when I start assessing my model, one thing I can do is I'll plot the fitted values and the residuals. And so here's the residuals on the vertical axis. Here are the fitted values. I don't want to see a trend in the dot. So here there might be a U. It is possible that there could be a U shape here when I'm looking at this, which could be a problem. Now here's a little trick. When you look at these plots, if you were to, in your mind, walk up, grab one dot, pick it up and move it to another spot, and that contradicts what you think you would see, then there probably isn't a trend. So let's say I take this dot here. If I would take this dot and move it here, visually, would I still see that U? Well, let's see. I don't think so. So I feel like there's not a pattern with these dots. Humans are very, very good at seeing patterns that don't exist. Humans are really, really good at visually detecting patterns. And that actually hurts us in statistics because we'll tend to see a trend that doesn't actually exist. And so I think this is okay. Now here we can use a normal QQ plot to check. Now here, this is an indication that maybe I don't have normalities. These are a little bit high above the line, but I think it's going to be okay. This is within reasonable bounds. Now we can run ANOVA also. So the summary function gave us the ANOVA output. But let's say I actually want to dig into the ANOVA table itself. Well, here, all I do is just run ANOVA on my fitted model, and we get our results. Now here for this part, um, I, I want to check to see, does it look like I have constant variance? Usually what happens when we have violations of constant variance, we'll see that as we go from left to right, our dots like spread out more. Like they'll be like, it'll form like this horn shape or triangle shape. When I don't see that, usually I'm pretty good on the constant variance, but I'm looking here and I feel like there's uh, that constant variance is a reasonable assumption. Now we can run the Durbin-Watson test for independence. And so this is a small p-value. So here, it looks like we don't have independence. The autocorrelation is at point, 0.36. Now this data set didn't, like, there's no necessary order on this. There isn't like a time aspect. So I'm just showing you how to run this code. So I feel like this is okay with this. But if I had like, if the rows of my data corresponded to the order in which I collected my data, there might be a problem with this. This would be enough for me to like, go, whoa, whoa, whoa. I need to back up and probably, you start using weighted least squares. And now here I'm plotting the predictor variable on the x-axis and the target variable on the y-axis. And here we can see that, the same model I had with the ggplot. And so yeah, I think it's reasonable. All right, so that's all I've got for you. So we talked about, simple linear regression. This is a very useful, very powerful tool. This is the mathematically simplest model that we can have for two variables. And that's all I've got. Life is short. Do math.